like we are live. Let's continue. Let me open the table of content here. Okay, if I remember correctly, we are on chapter 20. Okay, wait a minute. We are on chapter 20 and on homework simulation here. Let me open that. Okay, this one basically how to make the page table smaller, right? In this chapter, I am trying to remembering what we have learned so far. To make page table smaller, because well, the linear page table take up too much space or something like that, and we have one page table for every process in the system. So there is that. That's why we want to make the page table smaller, and then a few, what is it called, a few solution is discussed in here, right? For example, like making the page bigger, and also using the hybrid approach, patching and segmentation. Okay, and then using multi-level page table. And if I remember correctly, the homework simulation here is using the multi-level page table. Okay. And then yeah, this is still multi-level page table. Okay. Only upon a TLP misses, the hardware need to perform the full multi-level lookup. On this page, we can see the cost of our traditional two-level page table, traditional memory access, to look up a valid translation. Okay, and then there's also inverted page table. Instead of having many page table, one page table per process, something like that. We keep a single page table that has entry for each physical page of the system. The entry tells us which process is using this page and which virtual page of that process maps to this physical page. Finding the correct entry is now a matter of searching through this data structure. A linear scan would be expensive, and thus a hash table is often built over the base structure to speed up lookup. Hello Luigi, what's up? Welcome back. Okay, we are still learning about operating system with this book operating system 3ECPs. And still on chapter 20, about patching, smaller table here. And the last time we are on the homework simulation. But yeah, I'm trying to revisit for a little bit here. A linear scan would be expensive, and thus a hash table is often built over the base structure to speed up lookup. The PowerPC is one example of such an architecture. More generally, inverted base table illustrate what we have said from the beginning. Base table are just data structure. You can do a lot of crazy things with data structure, making them smaller or bigger, making them slower or faster. Multi-level and invert base table are just two examples of the many things one could do. Right, basically, patching mechanism here is about the virtual memory. So managing the memory, something like that. And then there's also this swapping the base table to this. Finally, we discussed the relaxation of one final assumption. Thus far, we have assumed that base table reside in kernel own physical memory, even with our many tricks to reduce the size of the base table. It is still possible, however, that they may be too big to fit into memory all at once. Thus, some systems place such base table in kernel virtual memory, thereby allowing the system to swap some of this base table to this when memory pressure gets a little tight. We will talk more about this in a future chapter, namely the case study on VAX or VMS, once we understand how to move paths in and out of memory in more detail. Okay, yeah, basically I guess the swap partition, something like that. So we put the page table to the storage disk, maybe something like that. Okay, and then summary. We have now seen how real page tables are built, not necessarily just as linear arrays, but as more complex data structure. The trade-off such table present are in time and space. The bigger the table, the faster a TLB miss, or translation look aside buffer miss, can be serviced, as well as the converse. And thus the right choice of structure depends strongly on the constraint of the given environment. In a memory constrained system, like many older systems, small structure makes sense. In a system with a reasonable amount of memory and with workload that actively use a large number of pages, a bigger table that speeds up TLB miss might be the right choice. Okay. In memory constrained system, small structure makes sense. In a system with a reasonable amount of memory and with workload that actively use a large number of pages, a bigger table that speeds up TLB miss might be the right choice. With software managed TLB, the entire space of data structure opens up to the delight of the operating system innovator. Hint, that's you. What new structure can you come up with? What problem do they solve? Think of this question as you fall asleep and dream the big dreams that only operating system developers can dream. Okay. So here, I think there is this aside, not that one, that talk about, where is it? Oh, this one, I guess. So there is a case where we have the multiple page size. Okay, so some application can request large page directly rather than using the default page size. Something like that. Okay, let's check out the homework simulation again, I guess. Okay, issue of implementation. Practical transparent for super page. Oh, okay. Yeah, this is the homework simulation. Wait. I think in this one. Okay. What is it again? In small tables. Right, previously we already try how to interpret the simulation, which is quite a lot of tasks, I guess. Yeah, if let's say I run something like this, I think at least 3, right? Let's say we have this virtual address. We can get all of this information from this page, something like that. And that make me kind of wondering, is the value here is the real value or the address? Yeah, I guess that's what I wonder off stream, right? Is the value in here the actual value or the address value? So I'm assuming it is the address value. I mean, can I assume all of this byte is the address, the memory address, something like that? I mean, what is it called? Maybe let's take this for example, right? We are in the page 78, right? Oh, we are in the page 78, and oh, I haven't, okay, yeah, I haven't put the page 78 there. Oh, why is it page, okay, page 44 is this one. Let's take a look at the page. The page 78 then. Not that one. 78. Yeah, maybe this one. Okay. This is 1 byte. This is 1 byte. Something like that. And then the offset is 21. Oh, wait a minute. The offset is 21, so it is in here. So this means that the address value, that the value is in address 1C, something like that, as far as I understand. Not 20, is that 20? Yeah, 21, not 20, not 20. Offset from here. So that's what I'm kind of curious. What is the value here? Like this one. I'm assuming this is the address in this byte. And now let's take a look at the readme here. This one, according to this, shows the 32 bytes found on page 0, 1, and 2, and so forth. The first byte, or the 0 byte, on page 0 has the value this one, and the second is this one. This is the 0 byte, this is the 1 byte, I guess, or the first byte, the second byte, and so forth. So I'm assuming this is the memory address for this byte, maybe something like that. Not necessarily the actual value. Maybe. And then we need to access this. What is it called? We need to access this virtual address to get the real value, right? Something like that. So in this case, in this virtual address, we need to access this virtual address to get the value. if I understand correctly. So yeah, there is a lot of stuff going on here. Okay, and then if that is the case, let me check the question here. With a linear page table, you need a single register to locate the page table. Assuming that advert does the lookup upon a translation look-aside buffer miss, how many registers do you need to locate a two-level page table? A three-level page table. Single register to locate the page table. Assuming that advert does the lookup upon a TLB miss. Okay. So we are assuming we have TLB miss, I guess. I mean, if we have TLB hit, we just get the translation, I guess, rather than trying to locate for the page table. And then for the two-level page table, single register to locate that. At least from this one, right? Maybe three. Do you need to locate a two-level page table? I mean, with single register to locate the linear page table. To locate the linear page table. Let me try understanding that statement from here. Linear page table. So we have this one, page frame number, okay. Only need a single register. So maybe we only need to fetch one memory address. Maybe something like that. What is it called? Page table only need one register. Okay, wait. You need a single register to locate the page table. The page table. Locate the page table with a two-level page table. Yeah, I'm assuming why we only need one, because we have one this is called. We only need one reference to directly access this page table, to directly access the page entry. Why we need page table only need I'm not sure if this is true. Maybe because we only need maybe because we only need one reference, I guess. We can directly go into the page linear page table with one memory reference. I'm not sure if this is true. Yeah. And then for the two level page table, for the two level page table, to access the page table entry, I guess. To level page table, how many register we need to locate, right? We can directly go in to the linear page table with one memory reference. To level page table, my hypothesis is maybe maybe two, I guess. I mean one, or maybe three. One register for page directory and another register for the small page table here. I mean, if we only need one register for this to locate this page table entry, right? Maybe in this two level page table we need to register, maybe one for the page directory and the other for the page table entry. If only need locate linear page table, then maybe we need to register to locate page table. One register. One register for page directory and another one for page table entry, the PTA. Maybe I think because we can directly not go directly get page table entry or PTA. On memory reference in linear page table. Yeah, I'm not sure if this is true. So maybe the register we are talking about here is about how many steps we need to access the page table entry. Maybe something like that. Yeah, I'm still not sure, which means I might be wrong. Alright. Okay. Okay. And then for the 3-level table, is it also 3? How many register to locate 3-level? I mean, if the 2-level a 2-level page table is something like this, right? If it is 3, then I might split this again. Maybe 3 register. One register for page directory. One register. Another one for another one for the sub page table, maybe something like that. Solve virtual address is 21-bit virtual page number component and 9-bit offset. Remember our goal in constructing a multi-level page table to make each piece of the page table fit within a single page. Thus far, we have only considered the page table itself. However, what if the page directory gets too big, right? To determine how many levels are needed in a multi-level table to make a piece of the page table fit within a page, we start by determining how many page table entries fit within a page. Hello cousin, welcome. We are currently learning about operating system by reading this book, Operating System 3 Easy Piece, and currently on chapter 20 and on homework simulation here, basically trying to understand about the multi-level page table, something like that. Given our page size of 512 bytes and assuming a page table entry size of 4 bytes, you should see that you can fit 128 page table entry on a single page. When we index into a page of the page table, we can thus conclude we will need the least significant 7-bit. Okay. As an index, how many bits left into the large page directory? Okay. Oh, page directory index 0, page directory index 1, and then page table index. Okay. So it looks like we still call this page directory. Okay. So maybe one register for this page directory index 0 and then another one for this page directory index 1, and then the last register is for the page table index. Maybe something like that. For maybe let's call it sub page directory, and the last one for page table entry. Again, I'm not sure if this is true or not, but for now this is my assumption or hypothesis. Okay. So does that mean the register we use will increase with how many level page table? Does that mean I register use is increased as the level of page table increase to let me check. Is register use increase as the level of page table increase. Are you in uni? No. I just learning this for fun, I guess. Okay, page table register. You only ever need one register which point to the top level page table. Oh, interesting. I just learned about memory management and I am currently trying to figure out what page table is. For my understanding, page table is a data structure that works just like hash table, used to map and connect both logical and physical memory address in an operating system. Okay. We will need one register to determine the location of a page table of a process. We will need one register to determine the location of a page table of a process. But how many registers do we need to determine the location of a multi-level page table? For example, a 2 and 3 level page table. How do you determine it? Also, how will gates L1, L3 in the processor affect memory reference access to page table? Will the majority miss or hit? Why does it happen? I tried to find reference for this, but it leads me to transaction look aside buffer and I haven't learned about it yet. Mike said that I'm really beginner in operating system. Help. Okay. You only ever need one register which point to the top level page table or page directory. The entries in the table are pointers to the next level tables and so on until the lowest level, which contains the actual physical memory address. So even though entry level page table only has one register, and what about the second question? Yes, that is exactly what I mean. One register to point to the top level table, no further register needed for any additional level, no matter how many. Oh, the second question should really go in a spirit pause. It may have different answer for different architecture. I see. I have never thought that it was really that simple. Thanks. We start a new post to get to the bottom of the second question. Case in the processor affect memory reference access to page table Okay. You really might want to learn about the LP first, though. It's are not that complicated a concept. There's a different kind of case. Any answer you get is likely to mention them. They mean that the base table get access a lot less than you would guess. And so whether they get kept in normal memory cache is not as relevant. I did read the materials about the LP, but I think that this question is a lot more opinion based as I think it is, because truthfully our lecture hasn't taught anything regarding the LP. I only need one register at the top level of table, and the entries in the table are pointers to the next level, so there won't be any needs of more than one register in any level of base table. Is there any reference for this answer? And then that make me also curious. What kind of register are we talking about here? Is it the CPU register or something else? Operating system have concept of multi-level patching, but what I don't quite get is until when we keep doing patching. I saw some article which say keep applying patching on page table till we can fit it in one frame or one page, I guess. Is this true? I asked some people and they say it's wrong concept. Can anyone please clarify this doubt? It would increase credibility if you could also provide some standard resource, like a book of any author recognized by many universities, which mention about this, an answer with our case. An explanation would be appreciated. Okay. Let me read this first, I guess. The number of levels in a multi-level patching system is determined by the size of the virtual test space, the patch size, and the architecture of the system. The size of the virtual trace space, the page size, and the architecture of the system. In theory, there can be as many levels as needed to break down the virtual trace space, but in practice the number is limited by performance and architectural constraints. Okay, we can come up with a formula for this number of paging level equal bits in virtual trace divided by bits for table indexing. Okay, well, let me copy this in the chat. Is anyone wants to take a look? For 32-bit architecture, you have a 32-bit virtual trace space and usually the page size of 4 kilobytes that leave 20 bits for page table indexing. Base and limit register. Maybe I should try answering operating system. What register means? Maybe. Okay, let's take a look at this. Segment register. Registers are fundamental component in computer architecture, acting as the brain's immediate memory that the CPU used to perform operation. And let me copy this in the chat. To perform operation, this article delve deep into how registers work, their roles, and whether they can hold different values simultaneously depending on their use. We will explore the intricacies. Is that how you pronounce this? Intricacies of register operation, type of register, and their significance in modern computing system. In the realm of computer architecture, a register is a small, fast storage location within the CPU used to hold data temporarily during processing. Unlike RAM or cache memory, registers are directly accessible by the CPU, enabling rapid data manipulation essential for executing instructions efficiently. Registers are integral to the CPU's ability to perform calculation, manage control flow, and handle data processing tasks that are fundamental to computer operation. Is register only in the CPU? Tuh. Yeah, I'm kind of curious about that. Let me check this. A register can refer to any of the following: with a CPU, central processing unit, and memory. The terms internal register or register refer to the latches. What is latches? Okay, let me change this to... Oh, okay. Latches that store a single character. The register capacity or register size is the amount of bits in a register, is known as the register width. Instruction flow at a rate as large as the register size. Width is either 16, 32, or 64 bits wide. It can only handle data that are smaller than their bit size. For example, if a program is designed to process 64-bit instruction, a processor with 32-bit register would not be able to run that program. Smaller than their bit size. Okay. Register or product registration. Oh, okay. That's star. In computer science, okay. Let me copy this to the chat. Is anyone wants to take a look? Okay. Only need one register to access the top of the page table. Okay, so maybe Maybe for the question here, if linear page table need one register to locate the page table, how many register we need to locate the page table in 2 level or 3 level page table. You only ever need one register which point to the top level page table or page directory. The entries in the table are pointers to the next level table. Okay. We only need one register that points to top level page table or page directory. And those and the entries inside those top level page table or page directory are pointers to the next level page tab, next level table. Something like this, maybe. So regardless of the level, how many level we have, 2, 3 or maybe 4 level page table, we only need one register. Regardless of level, for how many level for the page table, to the top level base table or base directory. And the entries inside those top level regardless of how many levels for the page table, we only need one register that points to the top level page table or page directory. And the entries inside the top level page directory or page top level page table or page directory are pointers to the next level page table or entries. I mean, if it is only linear, if it is only have one level or the linear page table, I assume it will have entries instead of another page table. Okay, let me copy that reference. Yeah, if there is any, what is it called? If there's any reference that would be great, but it looks like we don't have the reference here. Okay, without any case of any kind. And a control register and fetch the highest level base table entry. Find the next level base table that, for example, from virtual test or highest level base table entry, and fetch the next level page table entry from the RAM. Okay. Latency and bandwidth. Bigger and more complex means slower. There's multiple levels. Okay, interesting. Yeah, let me copy this too. In the chat. Until the CPU reaches the lowest level base table entry. Okay, well, I guess let's try understanding this more on the next session. So that's it for now. Thank you for watching and see you next time. Bye bye.